Okay, so we will continue from what we were discussing last week. We were discussing box models. So, with the reference to so the box model essentially is a convenient way of handling transport of freight and transport of pollutants in a large system. So, in general, when you are trying to model a large system, the general rule of modeling is the following. So, if you have to define a system where a domain, system domain, where some process is happening. So, in the system domain, process could be material is moving from one place to another place, reactions can be happening, material is changing, transferring from one phase to another phase within this. And then your goal is to find out rho A as a function of x, y, z and time. This is general objectives. Subject to whenever you have x, y, z, you have this is subject to boundary conditions and initial conditions. So, this is a general problem definition. So, in a system domain there is an equation that will describe what is happening in the system. Okay. So, if there is a rate process or it's a transport, anything that happens, and then there is boundaries of this. So, if you look at then the system definition for say an environmental system for water, for example, if you take a lake, it is very nice, it is a very well defined boundary. We describe that problem because of that. So, it has some boundary, whether it is regular shaped or irregular shaped, it is some boundary. So, it is possible for us to model it. But when you have a river, it is a very large system, properties of the system change with x, y and z. So, the system itself, the system definition itself is changing as a function of time. For example, if I take a river and we discussed it last class. So, we have rate in coming minus rate out itself. So, we are talking about rate in, we use this term Q into rho A2. This Q is flow rate of water, that itself may be changing because there may be an inflow of some other stream and then equals say rate of reaction. The rate of reaction is now dependent on few other factors such as temperature or presence of a second compound or if we say rate of evaporation, it depends on the velocity of the water or velocity of air, whatever the conditions of mass transfer. We will get to that later, that is the reason we will not discuss this now, because these terms have to be defined and that requires us to look at interface mass transfer. We will do it in the next section. So, but this is the movement of chemical within a phase itself requires you to define these terms here, and so these terms can change over a period of time. So, that is why we use box models as a convenient way of describing what is happening in a given small region and then extending into the next and so on. So, the exit conditions of one box will become the input conditions to the next and so on. So, you will have a very large number of boxes. It is like solving a set of linear equations. So, you start at one point, end at one point, there is the boundary condition. You start with something, end with something, you know what is at the end point, it does not match, you go back and redo it. So, solutions are done like that. So, when you this kind of box models is used for water quality. So, there is a set of models. If you go to the EPA website, there is stream water quality models. There are a number of water quality models that US EPA has. So, each one there is one to call there is something called as Qual2K and there is Qual2E and a few other things. There is another box model called stream itself. The various agencies which EPA, various people have developed models and EPA has adopted them. So, they have used it. So, in this very important system definitions, you need to define the system. If you are saying I am using a box model, I need to be able to define the system. I need to define dimensions of the system minimum, right. So, because here the a lot of times what we are doing when we go to transport models, we are transport out of this system or into this system, we are working on a flux based approach. We do not work on rate based, because when we say instead of rate, we say the mass balance is written in terms of rate equals flux into area. The reason we do is, this is a convenient way of expressing mass transfer or transfer from different places, and when we are doing flux we need to define the area. The area itself will either mean delta x, delta y, or delta y, delta z, or delta x, delta z, any of these three things. So, we have a system like this which is defined. We say this is delta x, this is delta y, and this is delta z. So, depending on this surface area is delta y, delta z, this surface is delta x, delta y, and this surface will be delta y into delta z. So, depending on which interface are we using, we need to add that area. So, therefore, appropriately we need to calculate the flux. So, mass transfer flux in a lot of terms are mass transfer is estimated in terms of fluxes, because it normalizes the area, and for a good reason. We will see that later. And so, the rate involves areas, which means the rate, if you want to write a mass balance equation, you need to define the system. You need to know the volume of the system, of that system. So, delta x, delta y, delta z should be known. Now, this poses a problem in when we go from a river kind of system to air. The air, we do not have a physical boundary. The air exists throughout. We know it is the entire expanse of air. So, if we want to write box models for air quality, it becomes a problem. So, people do the box models for air quality. So, what they will do is, if I want to look at regional air quality, so again the same thing, right. So, if I am looking at a particular city, I want to know what is the concentration of some species in air here. I would like to find out what is coming into the city from somewhere, okay, and whatever is the sources that are emitting pollutants into this volume above the city, and what is being carried out, which goes to the next place then, and what is being exchanged with the upper atmosphere and so on. So, these are all these kind of processes that are happening. What is the exchange between the land and the air here, and what is, but very critical here, the city x and y dimensions of the city are known, it is geographical dimensions, but the z dimension, this one, there does not seem to be a very strict boundary for this. Okay. So, if you look at it, you can look at the sky, it seems infinite, it keeps going forever. So, how will can I even do a box model for this? Is it reasonable to even approach a box model? It is very complicated system. So, that is the reason we see air quality models have a lag period. Water quality has been going on for a long time. Groundwater quality models have also been going on for a long time, because it's a slower system, it is more defined. Only thing is you can't see groundwater, so you don't know where it is, but it is reasonably slow. So, you can make some assumptions and say that it is here and so on. So, its general principles are known. The air, it's very difficult to approach this thing. So, people have studied it a lot in the last few decades and come up with a lot of theory, and we will look at some of this. So, the first problem is there a vertical boundary to, when we consider, if you want to consider a box model, otherwise it is a lost case. We can't do any modeling of this nature. So, we have to go to a very generalized model. So, what I mean by generalized model, we will see what a generalized model means, okay, which means that you have to write the full mass balance in its full form and then integrate it, it will become a multi-dimensional partial differential equation, complicated equation with boundary conditions which you may not be able to solve. So, we will look at that, one of those cases how it turns out. So, it turns out that the vertical delta z, people then looked at what is the behavior of the structure of air over the earth's surface. Okay. So, if you want to consider it as a box model, our definition of a box model is everything inside is well mixed. So, is there a region above the surface of the earth where you can consider it as well mixed? Okay. So, now this is not the same kind of concept that we study in liquids. So, liquid interfaces have this system also, okay. But we do not use it in liquids often because the thicknesses of liquids are all finite. We know that we can model the entire system, but we have to invoke these kind of principles in air, because otherwise we will have no way of estimating air quality. So, there is at least some approach air of we have something that we can do in order to do it. So, the vertical extent to which you can consider your box model depends on what we call as a mixing height. So, there are different terminologies to this, and some of them may seem contradictory to each other. So, we will just go over that. There is something called mixing height, which obviously, as the name suggests, that this is supposed to be the dimension where your vertical extent of box model is. It is a mixing height, which means that a pollutant I drop at the surface will go and mix well into the rest of the mixing height. Okay. That mixing height is based on a premise, on an assumption that, say, this is the ground, this is soil, and this is some height here in which everything is well mixed. Whatever I add here, it is mixed, which means that if I measure a concentration of a pollutant here and I measure it here, it should be the same. That is the assumption that we are making, that it should be the same. So, this mixing. So, the next question that comes is, how is it mixing? So, you are saying it is mixing, why is it mixing? Okay. So, what is the force, what are the forces that will cause it to mix? The first question that we have. Mixing of vertical layers. What are the reasons, or what possible mechanisms by which this can happen? What is one mechanism by which this can happen? Mixing? Convection. So, one is convection, but what is convection? It is convection. Convection is a description of the process, right. Convection essentially means that this is happening. Convection means it is moving in circles. Why is this moving in circles? That is what is the question. Density difference. Why does density difference occur? Temperature difference. Is there another reason for convection? Huh? Flow. So, flow itself is a mechanical energy that is given to the system. So, it is generally observed that higher the mechanical energy, or the energy that kinetic energy that it has, it leads to higher degrees of convection. So, we have seen this in flows. So, this is in fluid mechanic theory. When you have a flow inside a so we have flow, normal flow, let us say you have flow, you have a surface. So, you have flow inside this thing. When you have very low velocity, it is generally seen that the fluid is moving in a nice an element of fluid. If I drop a fluid here, some element of fluid, which means if I have a tracer, if I can trace the fluid, it is going in a nice almost a straight line, very close to the surface, and far away from the surface it is slightly different. The reason it is doing something very close, if the fluid is coming in at very low flow rates, you also, if you increase the flow rate of this fluid, what is observed is that you are seeing this kind of behavior. The fluid starts, this is velocity V1, as velocity V2, where V2 is greater than V1, you start seeing some kind of equalization, energy tries to distribute itself and it moves this way. And if I go to another sorry, another higher velocity, this thing starts moving in this direction. So, if keep on going like this, say I go to V4, I get really large convections. So, generally the scale of convections, the scale of convection is the distance of this, the size of this, these are known as eddies. The size of these eddies are expected to be larger and larger as velocity increases, velocities or the flow increases. Okay. That is one theory. Second thing is, very close to a surface there is a loss of energy. So, if a fluid is coming in with this kind of structure, if it encounters a surface, it loses energy, and when it loses energy, its velocity drops down. So, when it loses energy, it is going to assume a lower velocity very close to a surface than it is in a region where it is away from a surface. So, for example, you may find that there is very large scale eddies here, but as you come close to the surface, the eddies may vanish completely and it may assume a very low velocity, and as it goes away from the surface, it retains its original structure. So, two things here. One is high velocity generally leads to larger eddies, higher convection. This is a general rule of thumb. There are exceptions to this, but you need other information for this. Okay. Second thing is, there is what is called as a boundary layer that forms. So, what we are talking about in this picture here is that if I draw a velocity profile of so, let us say that there is a let us not even consider this surface, let us say there is just a surface and there is fluid coming in here and it is coming in at some average velocity, it is coming in at some average velocity. So, it has all, let us assume it is uniform, so it has large eddies that are coming in here. The moment it hits this surface, what happens is this portion, so this is the portion that is coming and hitting here, they are all at the same velocity, but the moment this encounters this land, the land takes up some of the energy, just dissipates, energy is dissipated there, and therefore this reduces, the energy of this reduces, and it continues to go. The energy reduction results in a reduction in the velocity. When you say reduction in energy, it essentially translates to reduction in velocity. It is like friction. Somebody is running very fast and they come to a surface which does not allow them to go faster, they will slow down. So, it is like that, it is friction. In a very simplistic definition, it is friction. But the regions away from the surface continue in its original state. But this energy in this system is fixed, right. Therefore, as it moves further down, more energy loss is occurring at the surface, and therefore, the energy loss has to come from other layers. So, when you go that this one slows down even further, this one slows down and this one remains the same, and if it goes further, even this one really slows down, this one slows down a bit, this one is now here, the other one is here like this. So, it keeps on going. For this particular parcel of fluid, the energy per volume is fixed, the amount of energy is fixed. So, if it has to pull energy, this friction is withdrawing energy from it, from this parcel, this energy has to come from the top layers, and that results in a reduction in the velocity closer to the surface. So, this results in what we call as a boundary layer, as a velocity profile. So, if I plot the velocity profile for this kind of systems, if I am plotting the velocity profile here, the velocity profile is flat. As it enters, they are all the same, but the moment it hits it, what we see is the first one, this one reduces a little bit, but the rest of them are all the same. But as it goes further and further in, you will see that this reduction increases. This curvature increases. So, what we say, the region where the original velocity exists, there is a region where if you mark all these points where I am making it straight, what it essentially means is in this region there is a reduction in velocity. This is what is generally called as a boundary layer in fluid mechanics. This boundary layer is where we assume that there is a variation in velocity, there is a velocity profile, but in atmospheric sciences this boundary layer exists in nature. It exists because we have surfaces all around the world, right. The entire globe is a surface. So, there is already a boundary layer, the air is not coming from somewhere else, it is already there. So, there is a natural boundary layer that exists because there is friction on the surface. This friction varies from surface to surface. So, if you are on natural grass there is a friction, if you are on water there is a different kind of friction. So, if you are on buildings there is a different kind of friction, if you are on forest there is a different kind of friction. So, this boundary layer varies, that is one. It means that there is a velocity gradient. We have already mentioned that if there is a velocity, if the velocity is lower, then it is very unlikely to have very large convection. So, this is where the contradiction comes. Okay. What the boundary layer, boundary layer is the physical definition of boundary layer is this. There is a velocity gradient in within the boundary layer. This is the definition, fluid mechanical definition of boundary layer. But there is something, a term called as atmospheric or a planetary boundary layer. Now, if you look at it, this planetary boundary layer, sometimes people call it as a mixing layer and all that. These are not the same kind of definitions. This boundary layer essentially is this boundary layer. This boundary layer thickness should not be very high. But there is another boundary layer which they call as a planetary boundary layer, where that is slightly higher, where what they expect is that this entire region is well mixed, and that is used to calculate how pollutants move in the region above the surface of it. This one is useful in estimating fluxes of chemicals from some surface to the earth. So, we will come to that later. But the other definition that we have used is mainly means what is the mixed layer, which is is there a ceiling to the atmosphere by which you can assume that there is a vertical height, where I can assume that vertical height to calculate the concentration of a chemical in that layer. So to get that information, two things are there. So, now we know that the vertical height is a function of the convection that we have, and the convection has two forces to it. One is thermal, which is based on temperature difference that we have mentioned. The second one is mechanical. So, mechanical is mainly the wind, the velocity. Thermal is the temperature. This temperature difference. Okay. Now, in order to explain this, people have come up with a couple of terms. The first term in that context is to find out under what conditions does the thermal and mechanical forces, how do they influence the vertical movement of a pollutant. So, this is from a pollutant point of view. These definitions make a lot of sense when you are looking at pollutant behavior in the region above the Earth's surface.